The ultimate guide to database per service pattern in microservices. Let's get into it. I'm Chris Test. I'm a KMP developer. Tech support said they're coming out for that on Tuesday. I believe them. I really do. Then there'll be no more complaints about the crazy portal that's open. Today we're going to be reviewing a neat video I saw with some really great animations that really explains what Alan Kay was talking about, where each object, each thing in the system, can only be accessed through an API, and this thing in the system has its own database inside it, and you can't get at it from the outside. It has to come, except through the API. You can't directly access it. And it's not shared with anybody else, although maybe it could be. But it's really you're not really supposed to do that. It's really not a good idea. And Alan Kay kind of talks about this in a generalized abstract form. And now I've actually have a example from Igor Bugayenko, who showed us how to more code what Alan Kay was talking about in the style he was talking about, with each object has its own database. And I have an example of the implementation of that with my book system. I did it in Java and Kotlin, and it's on my GitHub. But it's hard to understand, like, what are you talking about? But when people talk about these microservices with each database per microservice, that's exactly what Alan Kay was talking about. Except they had to do this whole new terminology around it, which confused everybody. But it's basically the same thing Alan Kay was talking about. So yes, this is the pattern that he was discussing. Let's get into it. Let's watch along.
In a microservices architecture, each service is designed to be small, independent, and loosely coupled. But unlike monolithic applications where all components share a single database, in microservices, you don't want different services to share the same database.
Right.
Because it creates tight coupling, which can lead to...
Right. So if you want to update anything in here, all these other things may have to be updated, and that's tightly coupled now. Because I like to try to be pedantic, because the first time I heard this, like, what are you talking about? It's like, well, if you make a change in the database structure here, and that this thing is now using, well, all these ones are going to have to update it, and that's the problem. Now, it actually may be the thing you want. Maybe that's the way you want, but if for this thing called microservices, and this particular definition of them, where it was one database per microservice, which is really a better way to doing all this stuff. But the people are like, but it's not performance. Exactly. This is the trade-off between being extendable, modular, independently deployable, independent of languages inside it. Yes, the trade-off is going to be a little bit of performance. So where do you put that? Well, that's the real trick, isn't it? Where do you put it? What has to be coupled and what has to be decoupled? Which one? Because it's really hard to kind of fix that after the fact. That's the problem. Again, then how do you fix it after the fact? You made the wrong decision. How is that process managed? Woo-hoo. Now you're getting into it.
To performance bottlenecks, scalability issues, and difficult service evolution. This is where database per service pattern comes in. Each microservice owns its own database, giving it full control over its data, schema, and how it stores or retrieves information.
Right, and then whatever the implementation details are hidden, obscured, but there's an API that we all have to agree on. So we still don't solve the problem of like which one goes where. We're more like, okay, this one is contained. You can't get it from the other guys. It's a law and you can't break it.
In this video, we'll break down the database per service pattern with practical examples and address its pros and cons.
Yeah, give him a like and subscribe. He does some good stuff.
The database per service pattern means that each microservice has its own separate database. This isolation ensures that each microservice can be developed, deployed, and scaled independently.
Right. Exactly. That's as well if you build your application in this way, which Yegor Bugayenko shows you how to build your application. So when you want to split this stuff out, it's not a total nightmare. It's like, oh, I'm just going to take this little thing that's a module here. I'm going to put it over here. It's going to go use the API over the network as opposed to doing function calls.
Without having to coordinate with other services over data. By adopting this pattern, we eliminate the risk of changes in one service affecting others.
Right.
For example, imagine an e-commerce platform. You might have separate services for managing inventory, customer data, and order processing. Using the database per service pattern, the inventory service will have its own database, customer service will have its own, and order service will manage its own data as well.
Right, and everybody asks, well, what happens if you need the data over here from this? It's like you can either get it from an API call, right? which may not make sense. Or you cache the changes. So every time there's a change that the web goes, I was like, well, we updated this record. Well, there's a message that gets emitted out onto the bus, and everybody else that wants to keep their local copy of that thing gets updated. And you have to build this into the system that someone's customer information may change after the order is placed, etc., etc. Keep going.
This separation ensures that if you need to update the schema in the inventory service database, it doesn't interfere with the customer or order service database.
I didn't.
And there are several ways to implement this pattern and keep a service's persistent database private. In private tables per service pattern, each microservice gets its exclusive set of tables in a shared database, but those tables aren't accessible to the other services.
I mean, that's a great way to. Yeah, if you have one database, then you separate it out by tables. The individual tables are all private, and they all don't know they're not related to each other. If you wanted to do it that way inside of a monolith, because then when you can break those things out, it's not going to be a nightmare. It's going to be already broken out, pre-broken, pre-split up. But you have to be strict about the rules, because if the moment you're not, you're going to be coupled, and then it's going to cause the nightmare.
In schema per service, each service has its own database schema.
Yeah. He just has a table inside of a database that then you can share the same instance of the data. Yeah. If you do this and they don't interact, there's no direct links between these things. It's all done by API calls and listening to messages on a bus. If there's to be an updated thing, if there's a redundantly data here and it gets updated from outside, that's the way you handle it. And then you don't link them together though. You're just gonna with the performance, and there might there's a lag between when somebody updates it and when it gets. Yeah, that's right. That's the trade-off. And is it worth it or not? And as it gets to really depends on your UK use case and what your users want, what you expect about your problem solution space. Which is it? Where do you have to? Where's the value for your customers? What can you do for your customer that gives them the value that makes it sense to do one way versus the other? I know, it's like, well, we don't know. Do we know? How are we gonna know? Guess what the answer is gonna be. I know it's gonna be tough. We're gonna have to run the experiment. Well, what if it doesn't work out? Well, that's the risk we're in software development. I know, it's like, oh, that's risky. It's like, yeah, we could waste time. That's the risk. Welcome to the jungle, baby.
Multiple schemas can exist in the same database, but they are isolated from one another. And in database service per service pattern, each service has its own database server, entirely separate from others.
Right.
Regardless of which option
must be separate, meaning like no call, everything has to be separate, but we have an API call. So we can all access it. We have to be able to access it asynchronously, hopefully. Don't try and do it synchronously, like locking. You're going to get in trouble when you do that stuff in a distributed system. Let's keep going.
You choose, the services communicate through APIs, not through direct database access. And this keeps the system loosely coupled and
I just said that. So we're on the same wavelength. So we're feeling it. That's what's so funny about this microservices stuff is like once I started getting into what they were talking about, and then also almost at the same time studying Alan Kay's stuff, I'm like, this is what Alan Kay is talking about. Then discovering Yiga Boogie Yinka was like, yes, this is exactly what Alan Kay was talking about. And if you write your application, your monolithic application in this particular pattern, you can easily split off these microservices. That's the whole benefit. It's like, oh, that's why we want to do everything. Yeah. So we can split these things off and make it performant by scaling, not performant by direct access. I mean, that's a scale, buddy. You might get away with it for a couple times, like three, an order of magnitude. But once we go 2 orders of magnitude, no, that's gonna fail, man. And it's also gonna be a nightmare to update, but it's performant. No, stop. I know Bjorn made us got your static functions and static variables. It's just direct access. It's like no, that's called spaghetti code. It's been a failed concept for a long time. Function, considered harmful is basically the same stuff. Coupling, direct coupling. Let's keep going.
Shows that each microservice controls its own data, making the entire operation seamless. Let's say a credit-based financial
it's not seamless. Let's keep going.
Service requires comprehensive data about users to access their financial health or credit score to determine their capacity to repay loans. It aggregates data from various sources like financial accounts, assets, spending patterns, income sources, and existing loans. Now imagine if all of these microservices shared a single database. Every time a user makes a request, say to calculate their home loan eligibility, the services would need to aggregate data from multiple tables, and this can lead to higher latencies and poor user experience.
Yeah, because everybody's accessing the same data store, as opposed to while the data is being updated, we kind of like propagate it out. is trying to get it all at the same time, all at once. All that stuff, that propagation that could have been happening, and littering out the each little update to all the different database stores. So when we go to ask for it, it's already kind of there in that service. That's the alternative. I know it's like, ooh, how do you get around it? No, there's just a trade-off, man. So that service that gets a credit score may be a little late, and there may be an update over there that takes an hour to get over to this other side for whatever the reason is. And that's the trade-off, as opposed to doing locked. And then it doesn't happen after you have the 10,000th user tries to access your system and everything's just deadlocked. That's the trade-off. Like for up to the 10,000 users, everything's great, super fast access. Oh yeah, but after the 10,000, it's like deadlocked. Well, how do we fix it? Oh my god, we have to totally revamp our entire system. How long is that going to take? 2 years.
In contrast, with the database per service pattern, each
we should have been more strict when we did it. It's like, with the performance.
microservice manages its own database based on its domain of function. For example, one microservice handles eligibility checks and another manages EMI or loan calculations. Each service has a separate database optimized for its task. So when a user checks its loan eligibility, the eligibility service queries its own database. If the user then moves to calculate an EMI, the EMI calculation service accesses its database independently. The separation reduces latency and improves overall system performance.
Right. Now, you're just pushing the latency of trying to get it all at once to, while it's being changed, just let me know and I'll keep an update here. And when you ask me for it, I'll just look at my update that I've already kept over here. But there may be other things happening at the same time, right? So that may be important to get those other things coordinated up. Like, that's the trade-off. And there's no good answer. It depends on what you're doing, right? So it's like this. People are like, well, which way do you do it? It's like, it depends. Tell me what you need. What do you need it to do? Which way does it go? Let's keep going.
One of the biggest challenges in using the database per service pattern is ensuring data consistency across services.
Right, data consistency. That was what I was looking for. Yes, your data may be inconsistent because you're not grabbing it all at once. At that time, we're taking all those. Even that data is going to be inconsistent. Let's be real about it. Even right after you collect all the data for that point, there could be an update right after that you missed. So you're not really getting away from it.
Because each service has its own database, maintaining data integrity can be tricky, especially when transactions span across multiple services. For example, imagine a user requests to apply for a new credit card. The seemingly simple action might involve several microservices, each with its database. Yeah. For example, user profile service stores basic user information such as name, address, etc. The credit history service maintains the user credit history such as past loans, credit card usage, payment behavior. Income verification service validates the user's income information. Credit score calculation service may analyze all data and calculate the user credit score, and credit card application service handles the actual application process. Now, suppose the income verification service successfully updates the user income in its database.
Yeah, we just talked about inconsistent updates. This is the problem this is the issue you have to deal with. So credit card application might have to do 2 checks. One at the beginning, get everything together, and then wait a little bit, and then ask again to make sure there was no more credit card applications. Like, that kind of thing might have to occur. Or you just like, well, we may have one might slip past the goalie. Let's keep
Credit score calculation service fails to recalculate the score due to a temporary network issue. Now, the user's credit score might be outdated, leading to incorrect decisions in subsequent credit applications.
Yeah,
also, imagine the user applies for a credit card and gets initial approval.
The other side of the risk is being so slow to respond by having all the perfect information that you'll never get the applications through. And that's just, I guess you'd have to. What businesses usually do in this case is like bake the risk into the cost of business and move on.
However, a final check with an external fraud detection service, say integrated with credit card application service, flags the application as potentially fraudulent. So if the credit card application service fails to update its database and communicate this to other services, the user might mistakenly assume that the application was successful. While the database per service pattern offers numerous benefits, it also introduces challenges.
Yeah.
Distributed transactions becomes complex since each service has its own database.
Right, but what's the alternative? Is there an alternative to doing it this way? Yeah, we have a mythical computer that has instantaneous compute power. Maybe. But even then, it's like, this is just like another one of those ontological questions. It's like we're reaching the limits of what is actually possible in reality with information and knowing things, and then but you can always just put the cost into the risk and just don't worry about all trying to make it perfect. Just, that's part of the cost of doing. There's gonna be someone that gets past this. How many? 0.1%, 0.01%. So and what are the costs? Well, you just integrate that in and move on.
Yes, requiring eventual consistency models instead of traditional transactions.
So
Data
so the trade-off is you'd rather process lots of people and maybe have a few slip by that get you, versus only process when they're perfect, and then people will just, there'll be a big line out the door just waiting, and the people will be just going. It's like, no, we can't wait this long for the perfect information. So that, and then you lose all of them, right? So that's the alternative. It's a business decision. I know it's like, I want it to be perfect. I want a logical. There should be a logical thing. It's like, no, not. There's sometimes just the limit. There are limits to what's possible for humans to know and operate. Like, it is possible to know. Wait there for 10,000 years, then we have the perfect information after 10,000 years. But those people are now dead. They don't want the loan anymore. They don't care about the loan. It's like, yes, but we know what their credit score is, down to 1/100th of a percent. Okay, but that's pointless now because they're dead. They've been dead for 5,000 years. Yes, but we know what their credit score is, and we know that we should not give them the loan. It's like, okay, well, that's super helpful. Next.
duplication may occur to improve performance, but it can lead to inconsistencies if not handled properly. Additionally, cross-service queries are tricky as you can't easily join data across different databases.
Yeah, that's right. That's why they has to have a data, a bus, an update. It's like each one of these things says, I just got an update. I just got an update. And everything says, who's interested in keeping their own little local copy gets that information. So, that bus has to be consistent. Now you're relying on that bus to be consistent and doing everything and make sure nothing gets lost or duplicated twice. So a whole other set of problems come into place. But that way, instead of having cross APIs, which could take a long time, you have your own little local database there, little sidecar. And, if you need to have something that's direct, real time, well, then you set that up differently. That's another channel. And you have to make sure the load is going to be able to handle whatever the throughput is, the scaling that you're talking about. Let's keep going.
Forcing services to communicate with each other to retrieve the necessary information. And to address these challenges, one can implement an event-driven architecture.
Yeah, you have to. This all has to be event-driven. Man, if you don't do event-driven stuff, you're totally missing the point. If you have these things just directly accessing, you're going to, might as well just have them directly coupled. I mean, you have to have an event bus.
Change occurs, like an update to income or credit history, publish an event. For example, the income verification service can emit an income updated event.
He just told me.
He's
telling me in detail what I just told you. Let's keep
credit
going.
score calculation service can subscribe to this event and perform necessary actions. This decoupled communication ensures that the data changes are propagated efficiently and reliably across the system. Do check out my video on event-driven architecture, where I break down the key concepts with examples from Netflix and Uber. You'll learn how they use event-driven systems to build scalable, fault-tolerant architecture.
And I also have a video called the Universal Application Architecture, which I show that how each one of these things can be represented as a person. If you think of the processor as a person, even like the event, like you get taking a phone call, and there's somebody there to answer the call and write down the message and put it in the log or the Excel spreadsheet for the processor to use. If you think of it as humans, because that's what these computers used to be humans. A computer was a person. I know this is hard to believe, but if you go watch that video, I go into detail why it's good to think about these things this way. So you'll just automatically understand. Yeah, somebody comes in the front door. The greeter goes, "Hey, what can I help you with?" And they said, "I got this." It's like, okay, well, go wait over there, and then this comes in the line. It's like you think of as people. Let's keep going.
Just ensuring smooth operations under heavy load. Many large-scale companies leverage the database per service pattern to ensure autonomy, scalability, and resiliency.
Yeah,
for instance, Amazon isolates data for different services to enable independent scaling, while Netflix empowers teams to own their data stores.
Right. I mean, that's the good part of it, but the other part is they may go off half-cocked and just go off and have things go use languages, use systems, whatever underneath it. Does this support it? Does it work? I don't know, but at least you can hopefully replace it easy. And then the battle becomes the APIs. Like, what are the calls and stuff? What are available for each one of these services from each other's services, and how to update the changing and modification of all that. It's just that's the hard part now. So you're not really you're not getting away from the complexity. You're just shifting it around.
This approach is ideal for highly distributed environments where microservices are deployed across multiple clusters. It allows each service to scale on its own, helping systems handle massive traffic volumes with minimal downtime.
Wow, you hope. That's the plan. I mean, there's really no other way to get to it other than to break it up into these event-driven systems at some point. But you can design your monolith in a way that when that day happens, when you have to break it out, that it's easier for you. It's easier on your transition, and your next version that splits that thing off. Or if it's just a piece of it you want to scale, it becomes really easy to scale that stuff if you build the applications in that way. Which Jaeger Boogie in my course, which I have below, how to program from the ground up, I talk about exactly what that is and the difference between the Bjorn Strustrup C++ Java class oriented programming, which is like just kind of like an extension of C, versus what Alan Kay and Igor Borgenko talks about, which is this back to object oriented programming, which is the original style, which is just this message chat passing thing. Whatever when they talked about in this video was about the message bus. That was the big idea, and then having each little organism, each little cell, only the API goes through the cell membrane, and the database is inside the cell, and you want something out of here, you're gonna have to get out of it, and then all the messages coming through the APIs in and out of through the APIs, and that's what Alan Kay was talking about. It wasn't objects or classes; it was this message passing thing. It wasn't. So that's what that's about. All right, give me a like and subscribe, and I'll continue my rants, and I'll talk to you soon.